So what happens if you have constant surface temperature instead of a constant heat flux? So what happens if the surface temperature of the pipe is constant? So it is constant everywhere. That means this delta T is gradually decreasing as the fluid is heating up. So let's say this is a cold fluid and this is a hot pipe. So the temperature will gradually decrease and eventually they may even merge. So that means the delta T is getting smaller and smaller. So how do we analyze this? So we have MCP delta T. So just like we did in the previous case, we have the control volume, this is dx. So we have Tm, this is Tm inlet, outlet. If this is differential, then we have dTm. The difference between these two is Tm out minus Tm in is equal to dTm as delta x goes to 0. Okay? So that means MCP delta T is the amount of internal energy change in the system, and that has to be balanced by the convection. H multiplied by T surface is the piped surface temperature, minus Tm, and multiplied by the surface area. And I can rearrange this equation. So I'll be doing a trick in here. So Ts is constant. Okay, so that means dTm minus dTs is equal to dTm. Okay, so that means I can replace, since this is a constant, let's say dx plus 2 is equal to dx. Both of them are equal to dx, right? So adding or subtracting a constant inside the derivative is not going to change anything. So what I'm going to do here, so I'm going to introduce a negative sign in here. So that means I'm going to introduce a negative sign in here, put a negative in front. So that means Ts minus dTm, this is equal to minus dTm, right? So minus we have positive dTm. So this is the positive dTm here. And then we have MCP, I pull them down in here. Ts minus Tm in denominator here. So I collected the temperature terms on one side, position term on the other side. And then you can integrate both sides, okay? And integrate it from inlet to exit. So T mean from inlet to exit. So integrate T inlet to exit. And this is going to be L inlet, L exit. So if you multiply it by L inlet minus L exit, multiply by perimeter, or multiply by dx, will give you the surface area. So log of Ts minus Te over Ts minus Ti is going to be H times As over MCP. And if you rearrange this exit temperature will be Ts minus Ti multiplied by exponential As over MCP. And so that means MCP is equal to H times As divided by ln Ts minus Te over Ts minus Ti. And by definition, Q is convective transfer is equal to H As delta T log mean ln. So if we use this equality here, so that means delta T log mean is equal to, so what is the delta T log mean that based on this equality? So that means Ti minus T exit divided by ln of delta T. So ln delta T exit over delta T inlet. Delta T exit inlet. So this is the log mean temperature difference. We talk about this in chapter 6, briefly, and chapter 7 also, and this is the derivation of the log mean temperature. So when you have a temperature variation, if the surface temperature is fixed, but the fluid temperature is changing, that means this difference is changing. So if you want to calculate heat transfer rate, HA delta T, this delta T is not constant. So that means I have to use an average. An average that I have to use is the log mean average.